Good morning, students. Today we are going to start the next unit, that is p block element. Students, in p block elements, the last electron enters the outermost p orbital. We can also say that the differentiating electron enters the outermost shell p orbital. As we know that the number of p orbital is 3, and therefore the maximum number of electrons that can be accommodated in a set of p orbital is 6. Therefore, students, the p block includes 6 groups from group 13 to group 18. It is interesting to note that the p block consists of both of nonmetals, metals and metalloids in the same block. The nonmetallic character of the elements decreases down the group. In fact, the heaviest element in each p block group is the most metallic in nature. Student, this group elements shows a wide variation in properties. For example, boron is a typical non-metal, aluminium is a metal, but shows many chemical properties, similarities to boron, and gallium, indium and thallium are almost exclusively metallic in character. The general electronic configuration of the elements of p block is Ns2Np1 to Ns2Np6. Hence, there are 6 families in p block elements. Non-metallic character decreases down the group. Students, the boron family has the configuration Ns2Np1, carbon family Ns2Np2. Similarly, nitrogen family Ns2Np3, and you can see that the electrons are increasing in the p subshell by 1, and we will have the oxygen family, halogen family and noble gas families. Today we are going to start the group 13 element, students, and in your syllabus in class 11th you have group 13 and group 14. So student, group 13 is the boron family. The outer electronic configuration of these elements is Ns2Np1. If you just see the electronic configuration, boron and aluminium have noble gas core. Gallium and indium have noble gas plus 10d electrons, and thallium has noble gas 14 plus 14f electrons plus 10d electron cores. So just have a look on the electronic configuration of the elements of group 13, which include, students, boron having atomic number 5, helium 2s2 2p1. So student, here we have written the condensed electronic configuration. Aluminium, it's a neon and 3s2 3p2 configuration. From gallium, students, we are having the, along with the noble gas configuration, right, we have the 3d10, that is d10 configuration is also there. So gallium has argon plus 3d10 4s2 4p1. Indium has krypton plus 4d10 5s2 5p1. Thallium has xenon 4f14 5d10 6s2 6p1 configuration. Now students, the occurrence, where do we find the boron family members, or where do we find the boron? Boron is fairly rare element, okay, right? So it's not the element which is present in excess, but it is present as a very rare element, and it occurs as orthoboric acid. Orthoboric acid, borax, then Na2B4O7.10H2O, carnite, Na2B4O7.4H2O. Students, the orthoboric acid formula is H3BO3. Right? The orthoboric acid formula is H3BO3. Then we have borax, its formula is Na2B4O7.10H2O. and the carnite, which has formula Na2B4O7.4H2O. In India, borax occurs in Paga Valley, Ladakh, and Sambar Lake, Rajasthan. The abundance of boron in earth crust is less than 0.0001% by mass. There are two isotopic forms of boron, 10B 19% and 11B 81%. Aluminium is the most abundant metal and the third most abundant element in the earth crust after oxygen and silicon. Bauxite, that is Al2O3.2H2, it's an ore of aluminium, and cryolite Na3AlF6 are the important minerals of the aluminium. In India, it is found as mica in Madhya Pradesh, Karnataka, Odisha, and Jammu. Gallium, indium, and thallium are less abundant elements in nature. Students, now we will discuss the variation in the properties. So first come the atomic radii. So moving down the group, students, you know that for each successive element, one extra shell is added. Hence, the atomic radius is expected to increase. But when we move from aluminium to gallium, right, so gallium atomic size decreases. This is because of the variation in the inner core of electronic configuration. The atomic radius of gallium is less than aluminium because of the poor shielding effect of D subshell. Because in gallium, we get the filling of 3D subshell, 3D10. So you can see that in aluminium, its atomic number is 13 and gallium we have 31. So gallium 31, so 10 elements of D block gets filled up before gallium. Right, so the 3D10 configuration, the D subshell will not be able to cover up the nuclear charge properly, right, and hence the nuclear charge will be executing on the outermost shell electron of gallium, and hence the atomic size decreases. Now coming to the student ionization enthalpy, IE or delta H, ionization enthalpy shows an irregular trend on moving down the group. Ionization enthalpy first decreases from boron to aluminium, but the next element gallium has slightly higher ionization enthalpy than aluminium due to poor shielding effect of D electrons, and then it again decreases in and then increases in the last element, that is the thallium. Student, the electronegativity down the group, right, down the group of electronegativity decreases from boron to aluminium and then again increases marginally, that means very fine difference will be there. This is due to the noticeable difference in the atomic size of elements. Now students, a very important we can say the effect is there, inert pair effect. The phenomena of electrons remaining paired up in the valence shell is called inert pair effect, or we can say that it is a reluctance or the inability of the s electrons of the valence shell to participate in the bond formation, and it occurs due to the poor or ineffective shielding of the ns2 electrons of the valence shell by the intervening d and f electrons. It increases down the group, and thus the lower elements of the group exhibits the lower oxidation state. That means down the group elements will show the oxidation state of their group, which will be low. Now the oxidation state. So from the configuration of the group 13, that is NS2NP1, they will show the +1 oxidation state as well as the +3. Boron and aluminium students show the +3 oxidation state, while gallium, indium and thallium, they can show both +1 and +3 oxidation state, though the stability of +3 oxidation state decreases down the group and the tendency to attain +1 oxidation state increases, right? So the stability of +3 oxidation state decreases due to the inert pair effect. right? So next, students, we will discuss the nature of the halides of this family, group 13. They are acting as a Lewis acid, right? So BF3, since it is electron deficient and it undergoes, the central atom undergoes the sp2 hybridization, right? So it will have the one unhybridized 2p orbital vacant. So ammonia, which is a Lewis base, will donate its lone pair to that vacant unhybridized 2p orbital and will form a coordinate bond. The stability in AlCl3 formed due to the formation of dimer. So AlCl3 stabilizes itself by forming a dimer. Students, you have to keep in mind that boron halides do not form the dimer because boron atom is too small to accommodate the 4 big chloride ion or the halide ion around it, right? So the boron halides don't form the dimer, whereas the aluminum halides, they exist in the form of dimer. That means the two units of AlCl3 will be linked together, will be in association with one another, right? The chemical reactivity of the boron family. Action of air. Amorphous boron on heating in air forms boron oxide, that is B2O3, but the temperature has to be kept high. Whereas aluminium reacts with the water water and air, that means moisture, and will form a protective layer of aluminium oxide. Similarly, the last element, that is a thallium, will also form a protective layer of oxides on its surface, and the element forms E2O3 type of oxides. Students, reactivity with halogens. Boron reacts with halogens to form trihalides. Boron B plus Cl2 will give BCl3. So they form the halides of the type EX3. Reactivity towards the water. So pure boron does not react with water, but with the boiling water it will react and will liberate out the hydrogen gas and will form hydroxide. Gallium and indium are not attacked by the pure cold or hot water. Thallium is little more reactive than gallium and forms an oxide on the surface. Students, the first element of the group 13, that is boron, right, it shows anomalous behavior. Boron is a non-metal while other members are the metal. Boron shows allotropy, right, while other members do not. Amongst the elements of group 13, boron has highest melting point and boiling point. Boron forms only covalent compound with maximum covalence being 3, while the other members form both ionic and covalent compounds. Oxides and hydroxides of borons are weakly acidic. Aluminium are amphoteric, while rest members are almost basic. Boron hydride, student, is quite stable, while hydrides of other elements are less stable. Only boron combines with active metals such as magnesium to form borides, while rest of the members do not. Crystalline boron is unreactive. So boron reacts with alkali to give the borates B plus NaOH, Na3BO3 plus hydrogen. Reaction with acids B plus HNO3 gives boric acid H3BO3 plus nitrogen dioxide. So you get the questions can be asked to you that how the boron reacts or what happens when boron reacts with sodium hydroxide or reacts with acid. Students, aluminium and other group 13 elements, the sum of the first 3 ionization enthalpy is less as compared to boron. This due to the easy tendency to lose electron, and it is able to form Al3 positive. In other elements, due to poor shielding effect of D and F orbitals, the nucleus hold the outermost s electrons tightly. Thus, only p bonding may be available. That is only since the s electrons are involved, are rightly held, so only p electrons will be involved for the bonding. In all the three elements, both +1 and +3 oxidation states are shown, that is aluminium, gallium and indium. The compounds in the +1 state are more ionic than those in the +3 state. Aluminium forms a thin oxide layer with dinitrogen at high temperature. They form the nitrides. The aluminium dissolves in mineral acids and aqueous alkalis and thus show amphoteric character. All the group 13 elements except the thallium shows reactivity toward the halogens. So this is a general equation, E plus O2. E here stands for the elements of the boron family. They are reacting with oxygen forming E2O3. Elements, nitrogen, right? It reacts with the element like aluminium. From aluminium reacts with nitrogen to form that element nitride. Aluminium with HCl, right? It forms Al3 positive, Cl negative, plus hydrogen gas is evolved. Element plus halogen will give trihalides. Students, the the boron trihalides, these are acting as a Lewis acid, right? And the acidic strength of these boron trihalides, right, it will increase down the group. That means if we have BF3, we have BF3, right, BCl3, BR3 and Bi3, boron trihalides. We are just moving down the halogen group, right? BF3, BCl3, BBr3 and Bi3, right? Among this, the stronger Lewis acid will be Bi3, and this can be explained through the p-pi back bonding. Now students, these are the uses of the group 13 elements. Boron glasses are used in making glasses, ceramics and in agriculture. Aluminium electrical devices and construction material. Gallium used as an amplifier, solar cells and satellites. Indium coating and alloys, and thallium in the photoelectric cell and toxics. Students, so go through this and just get it noted